No, no. I'll do that task. Because you are being made a co-host, no, so that you are
Okay.
able to talk and that's why that task we will be doing. You don't have to.
Okay. So can you see my screen now?
So we are
What
able
happened?
to see you, not screen.
Not the screen. I shared the screen.
No, sir. Still, we are not able to see you. See your screen, sir.
Oh. I entered them into setting, I guess. Yes, and I share the screen and start recording of asking with Zoom. Zoom will just put all the information that is visible on your screen. Yes, start now. That's what I did earlier also, but it's not getting into the.
Sir, you click on the share
This,
screen, then you will be having your PPT. They will ask what you
no,
want to
it,
share.
it says this permission allows an applet to show things on top of other applets you are using. This will interfere with your use of other applets.
So you can agree to that. To give permission for that. Have you opened something else also?
No, I just shared the screen, and after sharing the screen, it says this permission allows an applet to show things on top of other applets. This may interfere with your use of other applets. So, and then he gives no other option.
Okay, just give us a minute, sir.
This never happened earlier. This is the first time it happened.
Actually,
settings are going.
We also
Sorry?
did, so there was no problem actually.
How auto disable accessibility, Android Auto, and it's given camera and customized services.
Sir, are you doing trying to do that on mobile phone?
Yes. I'm sharing the screen. Again, it's asking the same. Is it because I am the co-host? Because previously I used to be the host.
Sir, I have made you the co-host only, and the thing is like our expert is saying you won't be able to share the screen on the mobile.
Oh my God.
All the permissions have been given from our side. So check your setting on mobile, please.
Okay, so
yes,
I won't be able to share the screen at all.
So you can try it now. They have given all the permissions.
Oh, okay. So let me
check the setting in your
share.
mobile phone that you are able to share the screen from your mobile.
Oh, how do I do that? Again, it's coming the same thing. Show system applets. Is it reset applet preferences?
Just click on the terms like agree or unagree kind of things.
No. There is no such option.
Okay.
Actually,
so what are the options are coming?
It says it just gives me list of applets, and it says that this permission allows an applet to show things on top of other applets you are using. This may interfere with your use of other applets. That's fine with me if it interferes.
So you can able to click on any option.
I'm able to see its accessibility. Then Airtel, that is my connectivity. then Android
Just click
Auto,
on
then
accessibility.
yes.
If there is
I
any
click.
option to click, then you can click this. Otherwise, your pop-up is blocked or allowed. There are two options. Maybe your pop-up is blocked in your mobile phone to share the screen.
So I should go to the settings.
Yeah. Otherwise,
Then
you can
after
use otherwise you can use laptop, please, because maybe
somehow I tried on a laptop. See, on the laptop I can't write. I'll have to write. I'll have to explain those
okay.
basics. So I need I can't type some of the symbols.
So you are using iPhone or Android phone?
No, I am using Android phone.
Android. So maybe in setting you may use your pop-up is allow. Maybe something is blocked in your mobile phone.
Sure.
Yeah.
But what is being blocked? I think if I go to Zoom and permissions,
Yes,
camera
sir.
and microphone, it says camera and microphone. Not allowed are calendar, contacts, files and media, and phone. So I think files and media. If I allow files and media, should
Maybe,
it?
so we can you can try it out.
Yes, I did that. I did that, and now again, if I share my screen, no, it's coming. It's again the same message. Camera okay, customize services. Find my mobile finder. I don't know why is it's not allowing me to share the screen. Previously, the other people also shared the screen, right? Let me try on the laptop. Actually, on laptop, I use Ubuntu. I don't use the Microsoft Office and other.
So once you check the Zoom setting, there is an option to access the photo or gallery. So maybe this option is blocked in your phone. That's it. In the Zoom app, you can check your Zoom app setting.
I'll just do one thing. I'll just give permission to every thing because it's too much of time consuming. Gallery. As such, I have started on my I have given permission to everything, and now your video is paused.
Sir, we are able to see your screen now.
Oh, okay, but I am not able to see Zoom now. Yeah. Yes. Okay, I saw. Fine.
Okay, sir. So
Okay.
the problem is solved now.
Yes. So I'll start with very basics. May I know how many you are extremely new to this area? Can you just raise your hands so that I can see?
Sir,
They don't even know.
majority is beginner. Yes, sir.
So I mean, should I start with basics
sir,
like even what is
Yes,
a
sir.
QRE vector?
Sir, let me introduce to you to the people, sir. Let the other
Yes.
people know who is the speaker. Give me some time, sir.
Yes. So should I wait?
Yes, sir. I am just waiting. Hello, everyone.
Yeah, you are audible.
Yeah, audible, na?
Yes,
Yeah,
yes, yes.
yes. Okay. Hello, everyone, and welcome to the day 1, session 2 The speaker for our second session is Professor Chetan P. Nevade. Professor Chetan P. Nevade is a professor in the Department of Applied Science, SR Group of Institution, Jhansi. He obtained his PhD degree from IIT Kanpur in the field of mathematics. He has an experience of 29 years, rich in industry, academia, and administration. Formerly, he worked as a registrar at PK University, Uttar Pradesh, professor at Galgotias University, Greater Noida, Deputy Dean at Lovely Professional University, and MTS at CDEC Pune, and many more. He guided various MPhil PhD theses. He has been invited as resource person in various refresher courses, FDPs, and workshops. His research interests include quantum computing, mathematics, optimization techniques, operation research, statistics, and cryptography. We welcome you, sir. Now I request you to start the session. Over to you, sir.
Yes. So let me begin with a very basic of quantum computing. There was a question: what is the difference between quantum computing and artificial intelligence, and also what is the difference between parallel computing and quantum computing? So if it is not answered, I think he has answered it. But let me tell you in short the difference. If you just Google it, you will see a lot of answers in the Quora. Here are some of the answers from the Quora. See this one. Can you see my screen clearly?
Yes, sir. It's very much clear.
See, this is quantum. If you see this middle message, quantum computing, it's all about zeros and ones, and sometimes both zeros and ones. From mathematical point of view, I'm giving you this difference. Whereas artificial intelligence is all about choosing either 0 or 1. And now how does that go? See, artificial intelligence actually tries to imitate a human. It tries to do things exactly in the manner a human would do. Whereas quantum computing speeds up the computation. Even the hardware required for quantum computing is different. In fact, that is the reason why most of the people left working in quantum computing, because there were some hardware issues in the 20s. There was some hardware issues. Now they have sorted those issues. So that is the reason why they were facing some problems with quantum computing. So quantum computing it's based on the quantum mechanics. See, it selects different states. It selects different states and gives you a combination of these states. It identifies different states, and then it gives a linear combination of these states. That's how it works, and that is the reason why linear algebra comes into picture. Do I make sense? I want it to be an interactive session, please.
Sir, can you just elaborate this thing a little more?
Yes. What quantum computer does is it identifies different states. While discussing the details, we'll see what a state is. And then it gives a linear combination of these states. So see, I don't want to teach you quantum computing. I want to focus on the mathematics involved in quantum computing. So where does mathematics come into picture? That's what I'm trying to tell you. Your quantum computing identifies different states in the computation, and it gives a linear combination of these states. It works with the linear combination of these states. And linear, when you use a linear combination, then linear algebra comes into picture. So that is the reason why you should know linear algebra while working with quantum computing. Is that point clear?
Yes, sir, it's clear,
Anybody?
sir.
Yes.
It's clear,
So
sir.
that's how, yeah, that's how linear algebra comes into picture. See, here it is. You can read it, but the thing is, if I go reading this, then it will be a long session. You can just read it. Quantum computing refers to the state of quantum computers. Quantum computers are a type of computer that utilize quantum states or superposition. In other words, a computer can be in a state between 0 and 1. This is in contrast to binary states used in the computers we have today, only zeros and ones. Researchers around the world are working on investigating what kind of problems can be efficiently solved using quantum computers. In contrast to quantum computing, artificial intelligence is the state of recreating human intelligence. That's the main difference. It recreates human intelligence. Although there are completely different fields of studies, they are completely different field of studies. They are related in that quantum computing could apply to achieve high performing intelligent machines. That's the similarity between them. Just a minute, I'll just adjust the screen of my laptop. It's getting blackout. Okay. So the last point, I think the previous speaker has already cleared that the quantum computing could be applied to achieve high performing intelligence machines. Researchers have suggested that quantum computing can efficiently calculate the global minimum of a function using quantum annealing. These are various terms that you would come across while studying quantum computing. Optimization methods are important in the study of artificial intelligence since they are used in machine learning algorithms to give computers the ability to learn from the data. Being able to do this efficiently will be a breakthrough in artificial intelligence. That's what the previous speaker was trying to clear, that after 1 week of training, you find some fault, then again you have to train the computer. Overall, quantum computer has no relation to artificial intelligence. However, they are related in that methods in quantum computing can be applied to artificial intelligence. Yeah. So that's the brief idea about this artificial intelligence. Parallel computing, of course, you people know, and quantum computing. So I'll just focus on the mathematics required for this quantum computing. So let me define this qubit. This qubit, if you go to these various sites, one of them I chose was Wolfram. This is really my favorite site for mathematicians. It's really a good site. mathworld.wolfram.com. Here you will find the definition of qubit. A qubit, or it's also called a quantum bit, is an analog of a bit for quantum computation. So previously, as I told you, in classical computing, we deal with choosing either 0 or 1. And whereas in qubit, quantum computing, it is either 0 or 1 or both, something wider. Unlike an ordinary bit, which may only assume two possible values, usually zeros and ones, a qubit may assume a continuum of values of the form from A to B. Do you know this notation? Do you people know this notation? How do I put on my...
No, sir. No, sir. People are not knowing.
You don't know that notation. Okay. Then, okay. Okay. I'll introduce you to that notation also. Uh, but uh, just to get an idea, you see, mod of a square plus b square is equal to 1. Mod of a square plus b square is equal to 1 is any number on the unit circle. It's any number on the unit circle. So let me get a whiteboard. This is my complex plane. And these are the set of all points which satisfy, suppose this is the point AB, then this point satisfied mod of a square plus b square is equal to 1. Right? This is my complex plane. And this is my complex plane. And these are all the values, this circle, unit circle, these are all the values which satisfy mod of a square plus b square is equal to 1. Do you agree to this?
Yes, sir.
So yeah, I have infinite values, right? Continuous values rather. So these qubits, they take values of this form, and therefore it's something more than just zeros and ones. It's much more. You have a lot of values. So that's what is being explained here. So let me tell you about the notation. This A is 0 and the other notation. I will share one paper with you. This is the article which gives you in short the basics. It gives you these basics in short. These are the basics it gives you in short. So Q computations. Here if you go bit, here it talks about Q computation. So maybe I can start from here. See, n will be a positive integer.
Sir,
N will
increase
be a
little
positive.
bit font size, sir. Please.
Okay, font size. Then I'll have to turn my mobile in this position. Then I can increase it as much as
It's fine, sir. Now, sir, you can little bit reduce, but it's fine, sir.
okay. So n will be a positive integer for us. You consider n as any positive integer, and j and k will be any positive integers between this range 0 and 2 raised to n minus 1. J and k will be any two positive integers in the range from 0 to 2 raised to n minus 1. And then let's see what this qubit is. What exactly this qubit is. consider this presentation. I have J equal to J1, J2, J3, J1, J2, J3, this. So how many values can J take? If I represent J as like this Ji is either 0 or 1. Ji is either 0 or 1. So how many values does this J take? If I represent J something like this, bit of length n, bit string of length n, then this J can take values from 0 to 2 raised to n minus 1. It can take values between 0 and 2 raised to n minus 1. Right? 0 is less than or equal to J is less than or equal to 2 raised to n minus 1. That's, I think anybody can understand this, because I can write J like this. I can write J like this. So this is very clear. Hello? Hello?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir. It's clear, sir.
Please, I wanted an interactive section. So I don't want anything bouncing on your heads. Okay. So now what I do, binary vectors, they are simply zeros and ones. Binary vectors are simply zeros and ones. Now just take b raised to n. B raised to n. That means there will be n tuples in this b raised to n. Take for example bq. Take for example this bq. So bq will have all 3 tuples, all possible 3 tuples. Okay. In particular, we will denote this tuple with 0 n. If you have come across this notation, this is what that notation is all about. And all ones are denoted by 1 n. So it's no mystery. It's as simple as that. What about the other values? The other values, they will be represented. Something using that notation that I was trying to tell you. Yes. Come here. Let's come here. I have this vector A of length 2 raised to n minus 1. Now I want to represent this value using this Q vector A. How do I do that? So this is how I do. Please. This is how I do. I write A as A naught times 1 in the first place and 0 elsewhere. Then A1 times 1 in the second place and 0 elsewhere. And lastly, 1 in this place and 0 elsewhere. So this A can be written in compact form like this. Where uj is the Q vector. These are Q vectors. This is a Q vector, this is a Q vector, this is a Q vector. These are Q vectors. So this A can be written in complex form as a linear combination of these Q vectors. And instead of writing uj, this q vector, we write it as this notation. That's it. We were talking about this notation. Remember that?
Yes, sir.
This is that notation. So what is this notation? It means it is the q vector where 0, 0, 0, 0, and this is 1 at the jth position. Jth position. At the jth position, we have 1. On the jth position, we have 1 and 0 else. So it is this notation. And what is the advantage of this notation? The advantage is I can write this A so easily as A is equal to this AJ into that Q vector. Let's take a very simple example to understand it further. For example, take n is equal to 1. When n is equal to 1, so we have 1 qubit. We'll take an example of 2 qubits also. And in general, you can imagine n bit. N qubit. N qubit. In general, you can imagine n qubit. So I'll give you an example of 1 qubit. So our n is equal to 1. N is equal to 1. So 2 raised to 1. That is, we will have only 2 vectors. My n is 1. So 2 raised to n gives me 2. So I have only 2 components. So I can write these components as 0th component, and this is 1 component. This is 0th bit, this is 1th bit. So I can write this A as like this. A0 at the 0th component, A1 at the first component. And if you remember, this was this Q vector and this was this Q vector. So this is just a simple example to understand the notation. That's it. Let's take an example of n is equal to 2. For n is equal to 2, so 2 raised to 2 will give me 4 vectors. 0th place, first place, second place, and third place. So any vector, say A, will be like this. 0th place, first place, second place, and third place. But we are using binary. So instead of 1, 2, 3, we will use this 0, 0, 0, 1, 1, 0, and 1, 1. Right? So this vector A is actually equal to A0, 0 times this vector, A0, 1 times this vector, A1, 0 times this vector, and A1, 1 times this. So I think the notations are clear now.
Yes,
What
sir.
is the
It's clear.
qubit?
It's clear, sir.
Okay. So I think now you should not be wondering if that word qubit comes. It's just a query vector. That's it. So that's all I would take from this article. It gives you some other basics also. If you want, I can share this. It gives you about the scalar product, then tensor product, and then some more things. So you can just graphical representation and all that. Okay, we can't discuss all of it here. The main thing I have already discussed. Okay, so now let me give you some other applications of mathematics. To start with, I've already told you about Qubit, so I'll skip this. There is another book I have collected. I purposely selected a book that you people generally would come across. Oh my God, why is this not rotating now? I have already. Okay, finally it rotated. There is one book. Can you read this? Mathematics of Quantum Computing. This book, Mathematics for Quantum Computing. Yeah, now it's clear. So I'll tell you about the mathematical contents covered in this book. What mathematics come into picture? So if I go to page number 12 of this book, we have some notations and references. Oh, sorry, I'm moving my laptop. I'm not moving this. Okay, here it is. These are list of symbols. Half of the mathematics lies in the list of symbols used. Once you are clear about the symbols, the half of the mathematics is clear. So these are the list of symbols. You see, I have already covered some of them. There is one symbol which you would come across frequently, and that is this notation. This is addition modulo 2. Addition modulo 2. And you know addition modulo 2, I guess. Everybody knows.
Yes, sir. Modulo operators.
You know, in general, it is addition modulo n. So it is the remainder when the given number is divided by n. So 5 mod 3, 5 mod 3. When I divide 5 with 3, I get the remainder as 2. So 5 mod 3 is 2. So addition modulo 2 will give me either 0 or 1. If it is odd, it will give me 1. If it is even, it will give me 0. So these are the list of notations given in this book. I will share this book also.
So what was the second notation?
Multiplication modulo 2.
Okay.
Okay. So this is multiplication modulo. So everything is calculated modulo 2. Here it.
Okay.
And then there are many other notations. GCD, LCM, prime power factorization, and then this is, I'll just point out some important notations. This is Euler's phi function. Has anybody heard of Euler's phi function?
Heard but do not remember, sir.
You don't remember? Okay. They are the number of integers, number of integers relatively prime to n. Relatively prime to n. Remember that?
Yes,
Some
sir.
of you might have remembered now. Yes. For example, let's take n is equal to some prime number. So how many numbers are relatively prime to n? And less than n, of course, less than p. So we have 1, 2, 3, 4, 5. All they are relatively prime to p because p is a prime. So we have p minus 1. We have p minus 1 numbers relatively prime to n. Agreed? If p is a prime, we have p minus 1 numbers relatively prime to p. If still not clear, let's take 5. What are the numbers which are relatively prime to 5? It's 1, it's 2, it's 3, and it's 4. None of them have anything common with 5.
Yes, sir.
Agreed?
Yes,
Yes.
sir.
So if n is a prime, my phi of n is p minus 1. If n is prime.
Okay.
Okay. Now if I take n as prime power, say p square. So if you see between 1, 2, 3, 4, p and up to p square, only p and its multiples, wherever they occur, they will have something common with p square. Rest, none of them will have anything common with p square. Can you see that? Again,
Yes.
let me take an example. Let's take p square is 25. So from 0 to 20, 1 to 25, 1, 2, 3, up to 25, the only numbers which will have something common with 25 is 5, then it's multiple 10, it's another multiple 15, and another multiple 20. Nothing more. Can you see that?
Yes, sir.
Yes. So we can modify this formula further and state that phi of p square is p minus 1 times p. P minus 1 times p. So phi of 25 is 20. You can see that it is 4 into 5. Correct?
Yes, sir.
Likewise, if you continue this process, say p cube and p square, p power 4 and so on. In general, phi of p raised to n would be p minus 1 times p raised to n minus 1. You can calculate that now. As we have calculated for p square, you can calculate for p raised to n. Can you do that? Try
Yes.
it. Okay, you can try that. So phi of the number of integers relatively prime to p raised to n will be p minus 1 times p raised to n minus 1. And now I go for combinations. I go for something like n is equal to p cube. I have p minus 1 relatively prime numbers for p and q minus 1 relatively prime numbers for relatively prime numbers for q. So my phi of n in this case would be p minus 1 times p q minus 1. again, you can check with example. Let's take a small number, say 15. So my 15 is 3 into 5. And the numbers which are relatively prime to 15, they are 1, 2, 3 is not possible, 4, 5 is not possible, 6 is not possible because 3 comes into picture. It's 7, 8, 9 is not possible, 10 is not possible, 11, 12 is not possible, 13, 14. These are all the numbers which are relatively prime to 50. So 1, 2, 3, 4, 5, 6, 7, and 8. So phi of 15 is 8. Phi of 15 is 8. And how do I get it? It's simple. It's 2 multiplied by 4.
Okay, sir.
Yes.
Fine, sir.
So, okay. So this is how I finally calculate for any given number integer n. I calculate phi of n as, let me check if it is given here. Oh, he just defined it, but he hasn't given the formula. The formula is if this is nu p. Oh, he has made it too complicated. So this is the first prime p1. Suppose I have n is equal to product pi to the power alpha I. Then my phi of n, number of integers relatively prime to n, will be, I extend that formula now. It is p1 minus 1 times p1 raised to alpha 1 minus 1 into p2 minus 1 times p2 raised to alpha 2 minus 1 into, and so on. I am just extending the formula we have seen before. Is it clear?
Sir, doubt. Sir, there is a doubt. Sir, you were saying if we are taking 15 and equal to p into q, and we were taking 3 and cross 5. So if we'll take
Yes.
20 and it's having multiple, fine. So we can take 5 into 4 also for 20, and we can take 2 into 10 also for 20. Then phi of n, phi of 20 will be equal to?
Phi, we are not talking about phi of 20. We were talking about phi of p square.
Yes.
We were
Sir, I'm
talking
talking about previous example. I'm talking about previous one. N equal to PQ, then phi of n will be equal to P minus 1 into Q minus 1.
Yeah, that's right. Okay, we were talking about phi of 15.
Yeah.
Yes.
I know that 15 is equal to 3 into 5.
So I'm talking, if we'll take 20 instead of 15.
If you take 20, okay.
Yeah.
Now that comes into this kind of example.
Okay.
Because my 20 I can write as 2 square into 5.
Okay.
So this formula applies. Corresponding to 2 square, I will have 2 minus 1 into 2 into 5 minus 1. So total it will be again 8. So phi of 20 will be 8. Let's take a bigger figure, say 48. Or is it clear?
Yes, sir.
Hello?
Yes, sir. Yes, sir. Yes, sir.
It's clear.
Clear. Yes,
It's
sir.
clear. Okay. So that is one important function, phi it's called Euler's phi function. And then we have this different other notations also. Order of an element modulo n. Order of an element modulo n. What happens if you take these all relatively prime numbers? They form a group under multiplication. So you should know what is a group. Have you do you remember that group rings and fields? Group, rings, and fields. Do you remember that?
Sir, listen, but I hope people are not knowing about these things.
Okay.
They might have
Maybe.
heard, but they may forgot for the timing.
Okay, I'll just recall the importance of. I won't be telling you the details. See, we have these integers, set of integers. I think everybody knows this set of integers. -3, -2, -1, 0, 1, 2, 3, and so on. Set of integers. This is the standard notation for set of integers. This is the standard notation for set of natural numbers. 1, 2, 3, 4, 5, so on. This is the standard notation for rationals. And this is the standard notation for real numbers. And this is the standard notation for complex numbers. Okay. So in this Z, we have those operations of addition, multiplication, the subtraction, division, and so on. Now, if you are given any abstract set, for example, in quantum computing, we are talking about the state. And now I have different states. So I have the set of all states. The set of all states. Now, this is absolutely an abstract figure. This is absolutely abstract figure. So, if I want operations on this abstract figure, then I extend this idea of operations on this via the group operations. So that's how we have a group G along with a binary operation star. Binary operation star. So it's a group G, and a group G is a set, any set, no restriction on what the set is. It can be set of all buildings in a city. It can be the set of polynomials. It can be any set, any abstract set. And this is a binary operation. If you remember what a binary operation, if you take an element of G, another element of G, then this binary operation gives you another element of G. So that's a binary operation. So this binary operation, if it satisfies certain conditions, then it forms a group. What are those conditions? Number one.
So can we take one example for this?
Let me give you the list of all
properties.
Conditions.
Yeah.
Conditions.
Okay. Sure.
This star is closed. That means when I take two elements of this G, then I must again get an element of G and nothing outside it. Star is closed in G. Second property is star should be associative. Star is associative. That means if I take any element A, I take any element B, and I take any element C and perform these operations in this sequence, this should be same as A star B star C. For example, let me complete the with take an example simultaneously. Take addition. Addition. The spelling is wrong. Addition. If I take the set of integers and addition on it, then addition of any two natural numbers give me again a natural number. If I have n1 plus n2, it's again a natural number. So addition is closed. Addition is closed in n. But now I take only set of odd integers. This is set of all odd integers. If I take an odd integer 3 and add another odd integer 5 to it, I get 8, which is not an odd integer. It does not belong to the set of odd integers. This is not odd. So addition is not closed. Addition is not closed in set of odd integers. Right? Is it clear? This property closed. You wanted an example.
Yes, sir. Yes, sir.
So that's what we mean by closure property.
I think she want example for binary operation.
Binary operation. These are
Yes.
all binary operations. Addition, subtraction, division, multiplication. These are all binary operations.
Okay.
Addition. What does addition give? See, you have to give it two natural numbers. Say if I am talking about addition over natural numbers, you have to give it two natural numbers, 3 and 5 I had taken, and the output will be again a natural number. So that's a binary operation.
Sir, how these
Binary-
operations can be related to the quantum computing, sir? Means
These are tools. I mean, basic tools. Without this, you just cannot do any kind of computation at all. So that's how these. I'll tell you the relation. So when you understand this is what is this group is generalization of your concepts of addition, multiplication, subtraction, division, right? The group operations, they are generalization. Group operation is generalization. It's generalization of addition, multiplication, these operations on abstract group, on an abstract set. See, if it is a normal set, integer and rational and complex number and real number, we are fine with addition, multiplication, subtraction, division. But if it is a set of vectors, it is a set of polynomials, how do I perform addition, multiplication, subtraction, division? So I generalize this concept. I define an operation on it which will satisfy some minimum conditions. And those minimum conditions are closure, associative, existence of identity, and we also require commutativity. These are the 4 conditions. So once you have these basics ready, then you can make some developments. For example, take for example codes. You talk about codes. Do you know what are codes?
So is it the programming code that you're talking about or some other codes?
No, some other code. Some other code. It's not a programming code.
So the encoding schemes?
Yes, yes. The encoding scheme goes through something called codes.
Yes. Hamming code and all that.
Exactly, exactly. That's it. So what are these codes? You were asking me the question, why all these, how is it used? Correct? That was the question. So if you see these codes, mathematically, what are they? These codes are nothing but codes are subsets of vector space. Subsets or elements. They are elements of vector space. And these are not real vector spaces. These vector spaces that you talk about, they are not real. These vector spaces are defined over some abstract structures like ZP. They talk about ZP, set of all integers, modulo P, ZP. This is set of integers modulo P, set of integers modulo P. So they are 0, 1, 2, 3, up to P minus 1. And your codes, these codes, they are vectors. So they are vectors, something like this. And these entries, this 0, 1, 2, 1, these entries, they come from ZP. For example, here these entries are coming from ZP. 0, 1, 2, 3. Sorry, 0, 1, 2. So how do you deal with these codes then? So you should know this modular operation. Modular operation. Then you should know these group operations. This is a code. Code means a vector space over a field or over a ring. So you should know what is the mathematically a vector space.
So there is a question from Mr. Muzammil that how many elements are in vector space?
Oh, that depends on what field you are talking over. This is vector space over a field. Over a field. If F is infinite, definitely vector space will have infinite elements. But if you have finite elements in this field, so that's where finite fields come into picture. Finite fields. We know infinite fields. You know the set of rationals. Everybody knows the set of rationals. Everybody knows the set of reals. Everybody knows the set of complex numbers. They are infinite fields. But what if these fields, they are finite? Something like ZP is finite. For example, your binary, it is Z2, 0 and 1. Z3, it is 0, 1, 2. So let me answer your question. How many elements does the vector space has? So it depends on the dimension of the vector space. We have dimension. And it also depends on the field. So suppose the dimension is 3 dimension or 2 dimension. Let's take 3 dimension. 3D vector space over, say, Z5. So how many elements can this vector space have? I have 5 components. Each one can take 5 values, 5 values, 5 values. 3 dimensions. I took 4 dimensions. Okay. I should have taken only 3. Okay, only 3. Only 3. So 5 values in the first place, 5 possible values in the second place, 5 possible values in the third place. So together I have 5 into 5 into 5 possible elements. So 125 possible elements. Does that answer your question? Just
Yes,
raise
sir.
your hand. Okay.
Yes,
So
sir.
this is how you are going to calculate the number of elements in a vector space. So you should know vector space. I don't want to discuss the details of this mathematics. I just want to tell you how this mathematics comes in picture of quantum computing. Okay?
Okay, sir.
So you see, you should know finite fields. And then we have cryptography also. The book which I am telling you, it doesn't talk about something called discrete logarithm problem. See, the idea is you want to talk about quantum cryptography. So to talk about quantum cryptography, basically you should know what classical cryptography is. Because you are going to extend this classical concept further. Agreed?
Yes, sir.
Yes, you are going to extend this classical concept further. You are going to make it more efficient, you are going to make it more facility giving, and so on. So you should know the classical theory first. Before moving to quantum computing, you should know you are computing what. So that what talks about, say, RSA algorithm. So you should know what is RSA algorithm, then you can talk about quantum RSA. Agreed? If you don't know what RSA is, how can you talk about quantum RSA? And then RSA needs all that number theory. Slightly one which I discussed previously, modular operation. Then it talks about those order of an element in a group. So group theory, it turns out to be a tool for number theory. So you want to talk about the groups, you want to talk about the order of an element in a group. Then you talk about the inverses. Then you talk about those Euler phi function, and so on and so forth. So basically, let me summarize again. To do any quantum concept, you should basically know the classical concept. I have two examples. You are talking about quantum RSA, you are talking about a quantum discrete logarithm problem, then you are talking about quantum elliptic curves. So to know these to do quantum RSA, you should know RSA, and to know RSA, you should know this basic mathematics. Groups, rings, order, so on. Not only that, if you go deeper, then you need something called distance map. You talk about Hadamard distance. Have you heard of Hadamard distance? Hadamard distance. Have you heard of Hadamard distance?
No, sir.
No. Okay, that is a term that comes in coding theory. So coding theory is what? Coding theory is you have a message. This message is converted into known symbols or mathematical structure. And then this mathematical structure is transmitted via zeros and ones, and after receiving, it is again converted back to the mathematical structure, and again it is interpreted as a message. This is how coding goes. Here there is no cryptography. I'm not talking about cryptography here. Cryptography is something different. This is pure coding theory. This is absolutely coding theory. How to code a message so that a machine can understand it, that is coding. So we convert this message into some known mathematical structures, namely the vector space, the codes, and then we transmit this in the form of zeros and ones. After receiving that string of zeros and ones, we interpret it back as a structure, and that structure back as a message. Is that clear what coding theory is all about?
Yes, sir.
Yes, it is converting a message into codes and then retrieving it back to messages. Why? Because codes are easy to transmit. Okay, you might say, what's the problem transmitting this message as it is, A, B, C, D? Why not transmit this A, B, C, D as it is? Suppose there is an error while transmitting. Anyway, you cannot transmit a A. You have to code it. You have to code it in zeros and ones. In zeros and ones. You have to code it in zeros and ones. Suppose you give an argument that, okay, I will code it as ASCII characters. And I will transmit those ASCII characters. But what are ASCII characters? They are simply a string of zeros and ones, nothing more. Suppose while transmitting, there occurs an error. Suppose there is a lightning. You transmitted this sequence, and because of the lightning, something like this goes further. How are you going to take care of these errors? So to correct those errors, I have to structure this message. And one of the ways to structure it is I put them as codes. And then, having converted them into codes, then I can have error detection. I can have error correction, and so on. Does that make clear the importance of codes?
Yes, sir. It's clear, sir.
Why? Yes. Why are codes required? Because whatever you can play with codes, you cannot play with ordinary data. That's it. Simple as that. And now, while playing with these codes, one of the concepts that comes into picture while this error correction and error detection is the distance map. And for distance map, for normal distance map, your metric spaces are sufficient. So you have metric spaces. What are metric spaces? They are mathematical structures which give you analog of distance map. See, if you give me figures like 4 and 10, what is the distance between 4 and 10? Answer is 6. Correct? The distance between 4 and 10 is 6. But now suppose I give you a polynomial x square plus 2x plus 1 and x minus 1 and ask you what is the distance between these two. What answer do you have? Do you have any answer? Are you following what I'm asking?
Yes, sir. Yes, sir.
Okay. So if someone gives you two figures and asks what is the distance between them, you can easily answer. But if someone gives you an abstract figure and asks what is the distance between these 2 points, I mean, you have no answer. So to get that answer, you have to associate with these abstract spaces a distance map and make it a metric space. So metric spaces, once you have a metric space, then you can talk about distance between these 2 polynomials. So that's how metric spaces come into picture. And further, deeper study would require something like Hilbert spaces, or in more general, you have something called norm-linear space. Actually, I am short of time. Otherwise, I had a full list of your quantum computing concepts and what are the mathematical structures involved into it. I'll give you in short, or I'll just give you a list. I won't be able to discuss in detail. So if you generalize that concept of distance, you get something called norm-linear space. And much further, you get something called Hilbert spaces. What are they and what not, that we cannot discuss now. I am just giving you an idea of how and where these mathematical structures come into picture. So these Hilbert spaces, they are very common. They are extremely common. They are used in construction of your quantum gates. Have you heard about quantum gates?
Yes, sir.
So while constructing these quantum gates, what is the logic? The logic which facilitates you the construction of these quantum gates, that is Hilbert space. I mean, it is one of the tools. It's not that once you know Hilbert space, you will be able to construct the quantum gates. No, to construct the quantum gates, one of the mathematical structure you need is Hilbert space. And in fact, your logical quantum rule for logical circuit uses elementary operations. So how much time do I have more?
Sir, it's already over.
So should I wind up in another 5 minutes?
Yes, sir, please.
You told me 1.5 hours, so I took for 1.5 hours. Okay, fine. Okay, so let me just give you a list of what is used where. As I told you, construction of logical circuits. They use Hilbert spaces. They need Hilbert space. What are Hilbert spaces? I don't think I have time to discuss what are Hilbert spaces. They are some mathematical structures. And in fact, even if you construct your quantum registers, they are constructed using quantum gates. and quantum circuits. So even for the hardware manufacturer, these Hilbert spaces are useful. And then in the beginning, as I told you, that these Hilbert spaces talk about transformation, transforms. You have to convert one thing to map one thing to another. Those transforms, they are studied through matrix operations. And the study of matrix operations, it's a subject called linear algebra. Linear algebra deals with the transform study and matrix operation. And I have already told you about vector spaces. Vector spaces. Sorry, I could not cover all the aspects because there are many other things that they talk about. They talk about probability also. In fact, that regression analysis, etc. This is all connected to probability. Regression analysis. Regression is finding the relation between two quantities. That is regression. I have already told you about number theory, and where it is useful. It is useful in quantum cryptography and many places. Number theory is extremely common. I had about a list of at least 30-40 areas of quantum computing and the corresponding mathematics it uses, but I could not even touch it. So I think I'll stop if you permit. If you have any questions.
Any queries from the audience? Any queries from the participants?
Sir, no query from my side. Like, firstly, I would like to say, like, in 1.5 hours, you explained really a lot, and we don't know anything about all these. Even I don't know anything about all these. But so I would like to ask you that in 1.5 hours, this much like understanding all these concepts was like almost impossible. So, do you have any MOOC course or any online content posted by you in any online platform where we can follow?
Yes. Actually, I wanted to read that book. See, I have already opened it. Can you still see my screen?
Yes,
Yes,
sir.
sir.
Okay. So these are some of the books that I have jotted down. Just one of them is Mathematics of Quantum Computing, and the presentation is too complicated. So I thought I would rather tell you. Oh, where did it go? Yes. So I can share this book with you, and you would naturally ask one question: why make things so complicated? The book has made some of the things very complicated. The reason is when you have to go beyond your uh, real things. As I said, when you have to work on some abstract structure, then you have to make things complicated. For example, if you see probability here, I don't know whether I'll be able to find this page or not now. Polly's group. So you see, this is about the groups that we are talking about. Elliptic curves. Well, this has a lot of mathematics. Let me tell you, this book has a lot of mathematics that is needed for quantum computing. But the presentation is too tough. Even for me, it was tough to go through at first sight, you know. So you can imagine one who is out of touch, how difficult it would be for him to understand directly from this book. But then you can Google and then get answers to some queries. So this will act as a guide. This will act as a guide. I want just a minute. I want to give you an example of that probability. He has made probability so complicated. Actually, it's not making it complicated. You have no other choice. You have no other choice. So it's around page 501. What page is this? Okay, 501.
So would you like to share this book with the participants?
Yes, I want to share it. Not only that, but I just want to guide you. Before you go through this book, you might get disgusted with the presentation. So I don't want that to happen. So that is the reason why I want to give you a bit hint. See here, they 500 and what was the 501? And this is 506. Yes. See, you see, everybody knows what probability is, correct?
Yes, sir.
But now see the definition of probability this fellow is giving. If you see the probability definition, see, a measurable P on a measurable space is called probability measure. Now this will really spin your head. If you take this as definition of probability, so what is this all about? It's that he has defined something like sigma algebra, and he is defining probability as a part of sigma algebra, as a sigma algebra. That's it. Nothing too complicated. Once you understand this, and why do you need sigma algebras? Because again, the similar concepts follow. That you have to measure something. Say you do integration, you measure the distance, you measure the size of a set, but how will you uh, make uh, how will you do this concept on an abstract set? So on an abstract set, you have to define analogous things. So here is something he has defined as measurable space, and probability comes out just as a one of the measurable spaces. So it's so the presentation seems to be a bit complicated. You need bit of maturity, but one of the good things is it gives you all the mathematics that is required for computing. How do I share this? How do I share this book?
Sir, there is one query.
Yes.
So Mr. Muzammil, he is working on quantum box. So can you please suggest any good book for topological transition in quantum box?
Topological transition
In quantum box. He wants you to tell him some good book for that.
See, this mathematics has nothing to do with quantum computing as such. It is a tool. You are using this as a tool. If you try to mix this quantum computing with mathematics, then you come up with such complicated conclusions. So I would suggest you to read topology separately as a mathematics book, and then whatever subject you are working in, You will understand it better.
Okay, sir.
Because if you directly go to what you are asking for, if you directly go and read those books, then you will face these kind of problems. You will need a guidance. You won't be able to read it all by yourself.
Yes.
But if you go through pure mathematics books, you will be able to read it by yourself. And then if you go for any work, then again you won't need any guidance. That's what I would suggest.
Okay, sir. Any other queries
So-
from the participants? So thank you, sir. Thank you, sir, providing the deep insights into the mathematical foundations of quantum computing. Thank you, sir. Thank you for a wonderful lecture, sir.
Okay,
So
thank you. Thank you, participants.
that's the end of the day 1. So we will meet again day 2, session 1 at 9:30 tomorrow.
So tomorrow's session is scheduled at 9:30 a.m. as the speaker is from the USA.
Okay, sir. Thank you, sir.
Thank you so much, sir. Ashish, session is over now. Okay, so tomorrow we'll start at 9 o'clock.